The second method of indirect proof that we will discuss in this section is called proof by contrapositive or contraposition. This method is typically used when we're dealing with expressions that have the following form. They are universals with a conditional. And the idea behind this section is to rewrite the conditional in the contrapositive form. And if you don't remember, the contrapositive of P implies Q is not Q implies not P. And in the logic chapter, we talked about how these two are equivalent. So if the first one is true, then the contrapositive is true as well. So if you're having a hard time proving the original statement, look at the contrapositive and show that it's true, and you automatically get that the original statement must have been true as well. So after you rewrite your contrapositive, you're going to be doing a direct proof, in which case you assume the not Q is true, and you try to get to the conclusion that not P must be true as well. So it's sort of similar to doing a proof by contradiction because you're going to be negating something, but here we're negating not for the sake of contradiction, but we're negating for the sake of getting the negative of P as well at the end. So let me explain by doing a couple of problems. So the first theorem I'm going to do is going to prove that for every integer n, if the n squared is even, then n itself must be even. This is a true statement. Now, why can we not do this problem directly? Suppose I assume that n squared is even, which means now I can write n squared as 2k. My job is to prove that n should be even, and in order to do that, it would require square rooting both sides. Now, there's no problem square rooting on the left, n comes out, but what happens when you square root the 2k? The problem is, it may or may not be an integer anymore. So like for example, if n squared was equal to 4 and you square rooted both sides, then you would get a 2 basically, or possibly a negative 2. However, if n squared was equal to 8, then the n itself would be 2 square root of 2, which is not an integer. So the issue is, we don't know what k is, so we cannot tell whether 2k is going to result in an integer when it's square rooted or not. It could be either way. So this is the reason why we cannot do this problem by a direct proof, and we will have to use the indirect method proven by contrapositive. Before I give you the proof, I would like you to try to find the contrapositive of the statement, if n squared is even, then n is even. See if you can jot it down on a piece of paper somewhere and maybe even start working on the proof. Figure out what the hypothesis is for the contrapositive and see if you can get to the conclusion. So here's a proof for the statement that we're discussing. First of all, I'm going to write the words proof by contrapositive. Again, there are very subtle differences between proofs by contradiction and proofs by contrapositive, so I would like to mention that at the very start so that the person reading my proof can kind of get into that mind setting to know what to expect next. And for you guys, it's a good idea to write the words proof by contrapositive or by contradiction or whatever at the very start. We're going to learn more methods later on, so there's going to be induction and so on and so forth. So please write down the name of the proof so that I know how to grade it, or you know what you're basically doing also. So let's take a look at the contrapositive. The original statement was, for every integer, if n squared is even, then n is even. The contrapositive will tell me that I need to swap the hypothesis and the conclusion and negate. So in other terms, I'm going to switch the n is even to the start of the conditional, and n squared is even is going to go to the end, and I'm going to have to negate both of those statements. And saying not even can be simplified as saying odd. So it's a little bit easier to write down if n is odd, then n squared is odd. So I'm going to do that to simplify the expression. And what am I going to do now at this point in time? I'm going to assume that I have an integer, and that integer is odd, to show, as a conclusion, that the square of the integer will be odd as well. So let n be an integer, furthermore let it be odd, just like the theorem wants me to do. And since n is chosen to be an odd integer, then by the definition of odd, I can rewrite it as 2k plus 1, where k is some random integer. So now I could go through the motions and square the n. In other terms, I can square the 2k plus 1, because that's what n is equal to in this case. By squaring and rearranging the terms, I can rewrite the n squared as 2 times 2k squared plus 2k plus 1 off to the side. Now remember, k is an integer, so therefore the parentheses 2k squared plus 2k is also an integer, because it's made up of products and additions of integers. Well, what does that mean? That means that n squared now has the form of an odd integer, which is what we want to show for the contrapositive. But if the contrapositive is true, then that means that the original statement is also true, because they are equivalent. They are expected to be equal to each other. Their truth values are the same. So that means that the statement in the theorem is true, and we are basically finished, because that's what we needed to show.